Hello, this is Shakil Ahmed. In today's tutorial, we will discuss about shape that is called Shapley Additive Explanation, which is a game theoretic and model agnostic approach in machine learning, explainable machine learning. Basically, most of the machine learning approaches are black box and we can't interpret the impact of specific inputs on the output or the response. So we need to we will attempt how we can explain the impact of one variable using the game theoretic approach that is called the shape value. So first of all, I just want to say happy World Statistics Day. Today is as we are celebrating the 20th October as the World Statistics Day. So most of the our audience are statisticians or data scientists. So it's your day and try to at least learn this beautiful and important topic. So we start with the Framingham heart disease dataset that consists of different demographic variables starting from age, sex, education, and smoking, and different clinical variables, biomarkers, including the blood pressure, cholesterol level, diabetic status, hypertension prevalence, and so on. So we will just discuss with the simple linear regression. First, we will discuss what is shape value and how it interpret the a black box type machine learning method. So in this tutorial, I will try to keep the things simple and discuss the uh, simple linear regression, and then the generalized additive models. That is also just a combination of different individual models we already discussed in previous videos. So we have already imported the data and check for the missing values. I have already some tutorials on uh, handling the missing values in the analysis. You need to check for the missing values and you should have complete data without missing value, at least in your exposure and in your uh, outcome. Then for handling missing values, we create separate vector and a matrix for quantitative columns and the qualitative columns, and then we handle the missing values differently. I will skip this portion. So now we get the data without any missing values. And for this, we start with the package sklearn that is used for most of the machine learning models, starting from linear regression. And the shape is used for interpretation that will help in finding the shape value. And that is basically the in case of linear regression, we say the expected value of y given x. For a specific value of x, we can find the uh, partial impact of the variable y variable, change in y variable when we intervene or we set some fixed value of x. So we will discuss this in this tutorial. So we have x and y values, and I will not use this data set. We will use the other data set. So I can just skip this. And then our data set is basically the DF we have already created. And I am taking the total cholesterol as Y and excluding total cholesterol. The other variables are uh, included in the X matrix. And for predicting the values, I use 100 instances as x100, that is extracted from the X matrix. And model, we are using simple linear regression model that is SKLN, linear model, and then linear regression. And the model fit X and Y, these need two inputs, one the matrix of X and the vector of Y. So we'll just we have run the regression model, and we can predict the values. And most of the important thing is we need to extract the coefficients, basically the partial effect of the covariates on Y, keeping all other variables as constant or zero. So male is minus 7.14. It means the cholesterol level for female is higher than male for this data set we obtained. And age is 1.2. It means for every increase in 1 year age, we have an increase of 1.2, whatever the unit of the cholesterol level is, we will get an increase of this much. And for education is also a categorical variable, and that is educated or uneducated, and current smoker. So these are the coefficients for these all these auxiliary independent variables, and this just denote the change in Y when we change a unit in X. Now we can just show the classical dependence for simple age. We can just see using this plot, shape partial dependence plot, and the variable I'm choosing the X age, and we are using model predictions, and we will get the predicted values of Y, that is called f of X, on age for every value of age. So age is starting from, for example, 30 to 70, and these are the expected value. This is just a straight line. Basically, we are running a linear regression. And this point basically is, this is the average value of age, and this is the predicted value of Y when age is at its mean value. For example, mean age is 48, I think 49 point something, and the average value of Y, average cholesterol level for the person with age, this is almost 235 or 237. So this is just simple interpretation of a simple linear regression for a given value of X. What will be the value, expected value of Y, and the line Y is equal to alpha plus beta X just pass through the origin and this line, and this is the mean values. This is a characteristic of the linear regression. So we come to the shape value, and we just see the game theory. In game theory, we have players and we have set of rules. So here we just connect the game theory with the regression problem. Here player means here we have the predictors. Predictors are the players, and the rules are the basically formulas are the rule. You can see whether this player can play or not based on the formula. So you can just see a feature to model function with the rule of the game. The function is the rules, and the predictors are the players. And then we have to decide whether a player is in game or out of the game, that we are including the predictor in the model or not. That depends on the basically how much contribution we are giving. The rules are incorporating an individual in game or not. That basically the function decides. So here, when we know the value of that feature, for example, that if the feature is observed, then we will say that this is included in the person, the player is included in the game, the predictor is included in the model. Otherwise, if the feature is unknown, for example unobserved, then that predictor is not included in the model. that player is not included in the game. So you can just uh, we have a set of players and we are having a game, and the game's outcome depends on all players, and all players are contributing to the outcome. So explainer, shape explainer, we are model predict x, and we get the shape values for a linear model using the shape explainer command. That is the predict model and x, and then explainer. So you can just run this and then plot age versus the uh, predicted values. So we are making just a partial dependency plot again for age and model predict, and the predicted values are basically we are just using 100 examples. Uh, we are taking a subpart of the x, and a model expected value and future expected value uh, on the x-axis, and model expected value is on y-axis, and then is equal to false, and shape values we are using the shape value. So shape value is basically this value is the shape value, and these are the shape values, and we can just denote some value here. So for shape value, the expected value of f of x is this. So you can just see, and again this line, the shape value of the shapes is uh, just we can see crossing the expected values. This is the expected value of age, and this is the expected value of y when age is at its expected value. So this is the same interpretation as we did here, and there is no difference in these two plots. But when we have non-linear functions, then it will definitely change. And we can just, if we want to see the shape values, we can just plot them individually using the shape plot scatter. These are the age and the shape value. So you can see these are the expected value of y for given value of different values of age. This is the same to this straight line. Now we will discuss the additive nature of the shape values. Shape values are basically the additive nature. For example, we have a simple value when no covariates, no player is in the game. We will get the some expected value of y. For example, for when age is 0, we will have some cholesterol level. Although this is not practically correct. When age is 0, there is a cholesterol level, but uh, we have other covariates that are unobserved, and we for the zero value of cholesterol age, we have the average cholesterol level, and that is at, for example, you can say 0.008. This is the expected value of y when x is 0. It should not be at 0.07. It should be something. I think these values still need to be updated. I think I was using different variable as a response variable. So we just run shape.plot waterfall. This is called waterfall plot, and this value is the basically the starting value when all the variables are 0, then we will, if we include this variable, the shape value increase by this amount, and if we will use this variable, then the shape value will be uh, will go to somehow down and then up. So it will collectively we will get the final result when we include all the variables in the model. So you can just see, now you can see at the initial we have 237, we have the shape value when all the variables are 0, 236.9. You can see this is the expected value of f of x when all the variables are 0. This is called unadjusted effect, unadjusted mean. And when we include other two features that have, these are just merged in a simple category, so we will we get a decrease of minus 0.02, that is decrease in the mean, so it's just going to downside. And then uh, we include glucose, it's just adding 0.17, and when we include diabetes, it's going 0.27 on this side. And then we include uh, blood pressure, then it's going median blood pressure, that is going this, and diastolic blood pressure, it's again going downward, and heart rate, increase in heart rate, it's again going downward. And when for a hypertensive individual, it's going up, so collectively it's going down. And for final value when we include age, it's decreasing by minus 9.12, that is the adjusted effect of age when uh, including all when including all other variables on these values. For example, systolic blood is at 108 and BMI is 21.59 and so on. So we are getting, and this is the total f of x, that is 223, and it was 236 when we include no variable. So this waterfall plot is basically giving the just the shape values, and these are additive in nature. And then we will do the same thing for a generalized additive model. I have already discussed what is generalized additive model in a previous video. Hopefully I will share the link in the comment box. So basically the generalized additive model run individual models on each variable separately and then add to a final model. So this is just same as the linear regression, but in linear regression we are putting all the variables at the same time. Here we are first predicting, uh, we get individual prediction from different single simple linear regression, and then add up to the final prediction. In this way we will get just a non-linear type of prediction. We just relax the assumption of non-linearity here, but still we are not including interaction, so these predictions are independent. So explainable boosting machine, you can just call the model as EBM, and we are using the linear regression without taking the interactions. So you need to import this interpret glass box. If the interpret package is not included in your already not installed, you need to install that. I have installed here, but I just silent this command. And then we just run a model with interaction as 0, and then fit with x and y, and then we will get the explainer again like above, and the shape value, and then we will get the dependence plot just like above. You don't need to worry about that, but the shape we are just plotting the shape values. but instead of a straight line we will get a zigzag line as the relationship between age and f of x is non-linear. In this case we are included all the variables in a non-linear way. And then shape plot scatter, you can just plot the shape values like we did for a simple linear regression. So now this is going somehow in this pattern, and this is again the expected value of y when age is on different scale. And then again we will make the waterfall plot for this non-linear model. We will again get this similar result. This is the value when all the variables are 0, and then the final value is now somehow smaller than the previous one. It's to 18.95, almost to 19. Previously it was to 22, I think. And finally, you can also see the individual, the effect of y for all individual values. These are the effects on the average value of uh, these cases. Now we will just find the expected value of y for all given values, for all individuals observations. For example, we have 10 individuals with different values of age, SX, and hypertension status, systolic blood pressure. So we will see the impact of the expected value of y, how expected value of y behaves. So these are the shape values, and this is again we need to update. You will get the shape value impact. These are just the impact of shape value. It's going downward or it's going upward, and this is just displayed for individual values. So you can see the from low to high. High is in red color and low in uh, blue color. So this is for basically instant level expected values. When we for every instant we will get an expected value of y when changing and these variables. So these are for different variables and these are for different instants, and red means an increase or a positive impact on the expected value, and blue means a negative impact. So this is just a brief introductory lecture on interpretable machine learning. I will discuss more about the interpretable machine learning in next video with different tree-based methods, or even if I have time, I will do for the neural networks like things. Thank you for your attention, and if you have any question or concern, you can always write in the comment box. Thank you.